First of all, I'm going to describe how to do that for a linear algebraic system. So imagine we have used all we have learned in this semester to discretize a partial differential equation into a linear system, ax equal to b. So this can be a huge linear system, but it's a linear system that describes the solution of a partial differential equation. And let's also imagine this right-hand side b is controllable. It can be controlled by a certain parameter. Let me just set as s. So s is my control. It can be the shape of my airplane. It can be the design of my jet engine. It can be the water injection schedule of an oil reservoir. Okay, and the solution x is the solution of the PDE. Let's imagine the quantity of interest j is also in this case a linear function of the solution x. So C transpose x. I mean everything is now in linear algebra. The question is, what is the best way to efficiently compute the derivative of the objective function with respect to s? And the setting here is usually the objective function is very low dimensional. It only has one quantity or a handful of quantities. For an airplane, maybe the noise, the drag. Right? For engines, it may be the thrust, how much fuel it burns, efficiency. So how do you compute the derivative of a handful of quantities with respect to a set of design variables, which is usually much higher dimensional? Right? If it's the geometry of an airplane, you can imagine it's a huge set of design variables. You can change essentially anywhere on the airplane or on the rocket that can affect your quantity of interest. So S is high dimensional, and J is low dimensional. Of course, you can find opposite cases when J is high dimensional and S is low dimensional. But in design applications, it is usually S is high dimensional and J is low dimensional. So how do you compute this sensitivity derivative, also known as design derivative, without having to solve the differential equation for or having to solve this huge linear system for many times? Yes?
Before going on, would you mind describing what J corresponds to in an example of an aircraft design with geometry? So you're saying S is corresponding to the design variables that you
right.
have, and then what would J then be in this case? The drag profile?
Exactly.
Okay.
So J would be, let's say, the drag, just one quantity, the drag of an airplane.
Okay. So one quantity you're trying to optimize.
Exactly.
Okay.
You're going to be optimizing one quantity. Maybe you are doing like bi-objective optimization. That'll be two quantities. But usually it's much lower dimensional than the dimension of the design variables. So how do you compute this design sensitivity efficiently without having to solve the differential equation for as many times as you have in the design variable? If you have, for airplanes, typically hundreds of design variables, the brute force way would be to solve the differential equation for hundreds of times. Each time you change the design variable a little bit and resolve the differential equation, right? And recompute the objective function. Is there better ways of doing that? So here, in this particular case, you can actually compute this sensitivity without ever having to solve this differential equation at all. Anybody think of how should I do that? You don't have to solve this particular linear system at all. Any ideas? Hint is you have to solve a different linear system. Yes? So let's say J is a scalar. I only have one quantity. How can you solve just a different linear system just once and compute all the sensitivity of one J with respect to all the S's?
Find something like partial x, partial j.
Can you find something like partial x, partial j?
Which is
So j depends on x, but x does
Right.
not depend on j.
Can we do like chain rule? Like, let's say dj ds is equal to dj dx times ds dx.
Good point. What if we do chain rule? dj ds is equal to
dj dx,
dj dx
dx ds,
dx ds. Okay.
and so dj dx will be the C transpose that matrix.
Yes. So this dj dx would be C transpose. So that is C transpose times dx ds.
And
All right.
solve for dx ds.
Okay, so the point is solve for dx ds. What is the dimension of dx ds? So remember, dx ds is not a vector, it's a matrix. Because there are many x's, there are many s's. So if you solve for that, you would be if you use iterative method, you would be solving this matrix A for many times. Yes?
You can solve the adjoint equation.
You can solve the adjoint equation. And what is the adjoint equation in this case?
So you solve A would be AX.
Let me use phi.
A phi equals C.
Equal to C. Okay. So imagine you solve this equation. So this is you call the adjoint equation, and I would make an important change to the system you are proposing to solve. This is A transpose. We are using the same A previously because we are assuming we have a symmetric bilinear operator, right? In the general case, if the matrix A is not symmetric, we need to put a transpose here. So this is the adjoint equation. And this is closely linked to what Xun was saying because this is almost there. Okay, I'm going to explain a little bit later. So if you solve the adjoint equation, why is it helpful? Because once you have this, you can plug this into J equal to C transpose X. Okay, the right hand side of the adjoint equation is C. So if you replace this with A transpose phi transpose X and take the transpose into the matrix vector product. If you take a transpose into a product, these two things would change order, so you have phi transpose times A transpose transpose, which is A, times X. Now you can group this instead. And what is AX? It's BS according to the original equation. So I have phi transpose times BS. Note what I've done here is I have completely circumvented the solution of the equation. I have written down a formula that directly links the right hand side of the equation to the objective function with solution appearing nowhere, right? Or through this formula, I don't need to know the solution to the equation to know the objective function. Of course, through this equation, I can compute partial j partial s just equal to phi transpose times partial b partial s. While this, what Shun has proposed, this is called the direct method of sensitivity analysis versus the adjoint method of sensitivity analysis. The direct way is more efficient if you have a low dimensional S and a high dimensional J. Right? Let's say I only have one S but many J's. Then it is more useful to compute partial X partial S first, because that's just the one vector, one solve. And then if I have many J's, I have many C's, and I can multiply partial X partial S by these many C's to compute the derivative of these many objective functions. The adjoint way is more efficient when you have a few objective functions J and many S's, because that way you need to solve as many adjoint equations as there are objective functions, and you can multiply these adjoint solutions with as many partial b partial s as there are design variables.